This is the second video under the video series Inscribed and Circumscribed Polygons. In this video, we are going to focus on special inscribed and circumscribed polygons as well as solve some problems involving them. First off, let us try to explore a special property of an inscribed equilateral triangle. We are going to see the relationship between the radius of the circle and the side of the equilateral triangle. For uniformity, let us denote the radius of the circle as r and the side of the triangle as s. Since the triangle is equilateral, we know that it is also equiangular. Thus, each of its angles measures 60 degrees. We will now draw the radius of the circle r, which also bisects one of the angles in the triangle. Thus, we have an angle which measures 30 degrees. We then draw the altitude of the triangle, which we will denote as h. Remember that since the triangle is equilateral, the altitude is also a median. Thus, it bisects side s into two congruent segments s over 2. We now have a 30, 60, 90 triangle, one of the special right triangles. Let us examine that smaller triangle further. As a property of a 30, 60, 90 triangle, we know that the side opposite the 60-degree angle is square root of 3 over 2 times the hypotenuse. In our case, that side is s over 2, so it must be equal to square root of 3 over 2 times the hypotenuse r. Simplifying that further, we get s is equal to the square root of 3 times r. In conclusion, we now know that in an inscribed equilateral triangle, the measure of the side s is equal to the square root of 3 times the radius r. Let's apply what we learned to solve the following problem. Find the length of a side of an equilateral triangle inscribed in a circle whose diameter measures 20 centimeters. The given r, the diameter is 20, therefore r, or the radius, is diameter over 2, which is 20 over 2, or 10. And we have to find the unknown, which is the side of the equilateral triangle inscribed in the circle. The formula that we derived a while back is s is equal to the square root of 3 times r. Using that formula, we have s is equal to the square root of 3 times the radius 10. That gives us 10 square root of 3 centimeters, the side of the equilateral triangle inscribed in the circle whose diameter measures 20 centimeters. This time, we are going to deal with circumscribed triangles. Recall that we can also say that the equilateral triangle is circumscribed about the circle. Let us explore the relationship between the radius of the inscribed circle and the side of the circumscribed equilateral triangle. First off, we can locate point S as the point of tangency between the circle and the triangle. We then draw radius US, and by properties of tangent lines, we know that US is now perpendicular to side PQ. We can also draw segment UQ, which bisects angle OQP. Since the triangle is equilateral, then we have a 30, 60, 90 triangle. In such a triangle, we know that the ratio between the leg opposite the 30-degree angle and the leg opposite the 60-degree angle is 1:2 square root of 3. From that property, we can derive the equation r over s over 2 is equal to 1 over the square root of 3. When simplified, this becomes square root of 3r equals s over 2. Simplified further, this becomes s is equal to 2 square root of 3r. In other words, the side of the equilateral triangle is equal to 2 square root of 3 times the radius. Let us use the derived formula to solve the problem. An equilateral triangle is circumscribed about a circle with the radius 4 centimeters. Find the perimeter and area of the triangle. The given is the radius of the circle, which is 4. The following are the unknowns: the side S, which is necessary to compute for the perimeter, and the area of the triangle. The formula that we derived is S is equal to 2 square root of 3 times R. Using that formula, we know that we can have S is equal to 2 square root of 3 times the radius R, which is 4. This can be simplified into 8 square root of 3 centimeters. Thus, the side of the equilateral triangle is 8 square root of 3 centimeters. Now that we have found out the side is 8 square root of 3 centimeters, we can use that to find the perimeter, because we know that that just is 3 times 8 square root of 3, or 24 square root of 3 centimeters. We can also use the side to find the area. So the area is equal to the square root of 3 over 4s squared, and that will be square root of 3 over 4 times 8 square root of 3 quantity squared, or 48 square root of 3 square centimeters. Thus, the desired quantities are the perimeter, 24 square root of 3 centimeters, and the area, 48 square root of 3 square centimeters. Before proceeding, let us summarize what you learned in your notes. Press the play button when you're ready. Let us also consider inscribed squares. Let us discover the relationship between the radius of the circle, r, and the side of the inscribed square, s. This is easier than our earlier derivations. We just need to draw diameter AC, which is essentially 2r. This diameter is also a diagonal of the square, which now forms a 45-45-90 triangle. In such a triangle, we know that the side opposite the 45-degree angle is equal to square root of 2 over 2 times the hypotenuse, which is in this case the diameter 2r. This brings us to the equation s is equal to the square root of 2 over 2 times 2r, which when simplified further becomes s equals square root of 2 times r. Thus, the side of the inscribed square is equal to the square root of 2 times the radius r. Let us use that formula to solve this problem. Find the area of a square inscribed in a circle with radius 5 square root of 2 centimeters. The given is r equals 5 square root of 2. We need to find the unknowns s, which is necessary to find the area. The formula that we are going to use is s equals the square root of 2 times r. We plug in 5 square root of 2, so we get s equals square root of 2 times 5 square root of 2, which is s equals 10 centimeters. Now that we found that the side is 10 centimeters, we can use that to find the area of the square, because the area is equal to s squared, and that will then be 10 squared, or 100 square centimeters. The area of the square inscribed in the circle is then 100 square centimeters. Let us acknowledge once again the developers of the GeoGebra app, which I used in drawing the illustrations in this video.